Yo, we're live. Um, Welcome. What's up? Today, we're working on the custom OS I'm writing in Rust, with the end goal of being able to uh, post in my own chat. So, what we have right now is we have a kernel that can be booted with QEMU, and I think probably can also be booted by like grub in a normal machine. But right now we've only been testing it in QEMU. And here we've like retrieved some info from the bootloader about our available regions of memory. And we're trying to see if we can get some sort of like memory allocation going. The idea being that if I have memory allocation, then I can do make use of things like hash maps and vectors and not worry about like managing stack frames and stuff. I just want to like be able to like work like it's a high level language, and I think that just getting us allocation gets us basically there. If I look through like the Rust standard library, the things that we're missing are like threading and like file IO, but we get like almost everything else, which is pretty sick. So what we have right now is in the last stream we parsed this info out of the bootloader. So there's this like multiboot standard, it's called. And in the multiboot standard, they say that they will provide your kernel with a bunch of info. And so in our case, we have this like struct that came out of multiboot, which isn't complete. This isn't a complete version of it. But what we have in here is like, oh, these are like the regions of memory we can map, and like this is our boot device, and this is the name of our bootloader. And so we confirmed last stream that like if we print this, we get QEMU, and if we iterate this, we get something that looks sane, right? When I ran this, these are like incrementing addresses with links that are like maybe sane. I think I'm just like eyeballing these, and I would like to get a better feel for what this adds up to. And yeah, so the goal for today, as was the goal for last stream, but we didn't make it, is to get some sort of like allocator going. And last stream we were thinking about doing this via like paging. So the kernel, what do I want to call this? Paging. So the CPU has this like concept of mapping virtual to physical memory. And you can like set up this page table or a page directory that's like a well-defined format that basically tells the CPU like, hey, when somebody accesses this memory address, actually go somewhere else over here instead. And I was thinking like this seems like it's the way to go. This is what like they recommend, and it would let us use something like a user space allocator like JE which is just like an alternative malloc free implementation. Like we could use this in our kernel. But I was thinking I would be kind of interested to know if we can get away with doing something way shittier. So I think the reason that we would want paging is to handle like one is like user space processes, right? You could like, if you have like 10 processes and and you're just like using memory directly, they can like clobber each other's memory, right? So like let's see. Right, like if I have like memory, this is like 0, and this is like big number. And process A is using like this chunk, and process B is using like this chunk. Without paging, I don't think that there's like a simple way to get like access control here. So I've like mapped this page to A, and if A just goes like, oopsies, I'm gonna go look at this. I think page faults are usually how you stop that. So you say like the CPU goes like, whoa, dude, you're not allowed to do that. And I think that's from page faults. So osdev wiki page faults. Let's see, page fault. Oh, this is only when they're not in memory. But I think I saw like security invalid protection fault, maybe segment error. Yeah, privilege type limit read write writes. Referencing accessing null pointer, writing a one reserved register, executing privilege. Okay, so I think I saw something about this. I'm not. This actually doesn't clear to me. if this is privileged. But in the paging section, I saw that you can like inject a process ID into the mapped pages. Page size, hold on. User supervisor read write p present. I thought you could put process ID, but maybe I misread. So, okay, that's one. If that's a reason that like this provides some sort of like user space memory integrity checks, for now I don't care, right? All I really want is to be able to use a vector in my kernel. And like maybe another reason is if I get like memory fragmentation, like I can map pages from physical to virtual memory, and then I can like have contiguous chunks of memory that don't need to be as big as like the that don't need to have like a continuous large space in normal RAM. And maybe another reason is if like I want to overcommit memory, and I think none of those really apply to me right now. I think that really all I want is I just want to use a vector. And so I want to see, maybe I come back, maybe I find out that this is like something that I'll want to implement for real. But for now, what if I just skip all this and make a really shitty memory allocator, right? Something that just keeps track of what physical pieces are free and just hands out physical pieces of memory. And I'm interested to see how far that gets us. And I think that nothing that we did last stream is wasted here, because we still have to make sure that like these sections that are given to us from the bootloader as like mappable segments of memory, we still need to make sure that we're like within those. So I want to take a look at this, see how far we get, and off screen since last time, I've done a little bit of work here. So one is that I split out some files. So before everything was just in main, and now things are split out. So like there's like a module for terminal writing, a module for libc functions that are required by the Rust core library, as well as I split out this like multiboot parsing into its own section. Hold on. I think that there. And then the big change that I made is that I found out that the core library implements this like write macro, the Rust core library. So if I look at like core write, this actually gives me like Rust style printf style argument formatting for free, assuming that my output implements this like core format write interface. So all I had to do was implement this like write stir function here, and I get formatting for free. So last stream we were like printing pretty manually. We were saying like, hold on, let's look at the multiboot. So here we were doing like writer.print i32 int, writer.print stir test, and then this was like a byte string, blah blah blah. But what we've done now is in the terminal writer, all we've done is just call this like write this buffer function that we already had, and we just take in like a stir and we turned it into a byte stream of bytes. So if there's like UTF-8 characters in here, they probably won't display properly, but I don't really care, right? And that lets me like say like I want to that would let me say like I want to call like write terminal test, like throw in some like a formatter string. I put in like this here if I wanted to. And then I went a step farther and I found out that, or I found a way to make terminal writer a like static function or a static object that's initialized once. And then I like created my own print and print line macros, which means that I can just now, if I want to say like print line high stream, as long as this happens after initialization, that shows up here now. And we get like we get all this stuff for free now. So now I can say like high stream, here's an int, and we'll just make that like that. And then we'll say here's a float, and this will pass in as like 1.1 plus 2.2. And here's a string, and we'll say, here's a str, and this is called y. And I think if I did this right, yeah, see? We say, hi stream, here's an int 3, here's a float 3.3, here's a stir test. And like all of that just comes for free, which is sick. I was pretty stoked on that. The other thing I did is I found out that I can actually use GDB with QEMU. So if I wanted to like take a look at like memory in my kernel, I can do that if I just say, let's just make sure that this has GDB in here. Just give me a sec. Start up a shell with GDB. Bump, 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 bump. Okay. I can call Rust GDB target debug kernel. And I could say target remote localhost 154. And I can break on kernel main. And now this is running. But nothing's happening yet. So if I like iterate over these until I get to print line, boom, stuff's printed, which is pretty sick. Pretty sick. Although it's kind of weird that some stuff happened out of order here, but that's out of order execution for you. And if I wanted to like look at the stuff in if I wanted to look at the stuff that's like provided to me by the OS, I could break it kernel main, and I could print info, and this will show me what's in here. Just pretty sick. And I can look at like, yeah, like this is just working. I just have all this stuff, which is sick. Sick, sick, sick. Pretty cool. Yeah. So that's off screen. What I want to do now is I want to just jump into seeing if I can get what's it called? The allocator working. So the first thing to do is we'll start by building the alloc crate from Rust. So I should build this. And then if I go to main, oops, there's already one over this. If I say, oopsies, extern crate alloc, we saw last time we tried this that it will get mad because there's no global allocator. So I need to add a global allocator. So what does it say? It says we need a global allocator that implements the global alloc trait. So let's look at what that does. Global alloc. Okay. Very, very cool. So we need to implement an allocator, and then probably we need to assign this with global allocator, which is a global allocator. So apply to a static register as a global allocator, okay? So let's try just making our allocator here. So let's make a new file called allocator. In main, we will use this. We'll go mod allocator like this. And here we'll use core. We need to use the allocator, the alloc trait. Global alloc trait was what they wanted. So we'll use core alloc global alloc. We'll make a new struct that implements this. So we'll just call this our allocator. And we'll implement the global alloc trait for our new allocator. And these are free, so we need to just implement these guys. And here we just go this, here we go this, and we say unimplemented. Because they're not, we don't want to actually worry about it yet. We'll figure this out later. And we'll make a way to construct this externally without knowing the internal details. So we say pub function new goes to allocator. And all this does is run allocator like this. And here in our main, we set up our global allocator as a global allocator, I think it was called. Static. We make it static. We say alloc, which is an allocator, which means that this needs to be exported as public. Equals allocator new. Okay. So probably this will fall over in some way. Let's see what happens. Okay, so first we need core alloc layout. This. It doesn't like this, so we need allocator like this. It needs an unsafe impl. And it doesn't like that this is a non-const, so we'll just make this const. Okay, so let's see if like our program still runs. We need to turn off the debugging stuff, so we'll go like this. And okay, so nothing crazy. And now I think it should compile if I say let v equals vec new. And I guess this is alloc vec new or something. And we'll make this v vec. I guess we just put something in there so that it knows. And make this mutable. All right. So now this should crash, but we don't actually have anything that's printing. So I think that we maybe if I go in here and I say like we panicked. Okay, sweet. So we actually do in fact get this unimplemented, and so probably it would be nice if we could know what happened. So let's print out the panic info. Core panic info. Returns the payload. This will commonly but not always be static string. Okay. Let's just throw this guy in here. This seems reasonable. Panic occurred. So here we actually didn't get the string. But if I say panic unimplemented, panic occurred. I expected to get this in here. So why not? Why not? So let's look at the panic macro and see what this actually does. Core panic. Panic's the current thread. This macro is the perfect way to assert it's blah blah blah. Unwrap method blah 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 blah. When using panic result. Okay, so what does this do though? You can override the panic hook using stood panic set hook. Can I just like print this panic info? Oh, we can use our fancy new debugger trick to see. So let's try that. So here we run qemu with -s. Then in here we run gdb on kernel on target debug kernel or something, and we break on panic. What I call my function? Do I need to do rust gdb here? B panic? Not defined. B main.rs45. Okay, let's just do that. Program is not being run. So target remote localhost 124. And so where does this come from? Okay, so this comes from my allocator implementation. And it calls panic format and calls kernel panic. So what's in my panic info? Why is it formatted like this? I wish that it was like nice and pretty. That's okay. We'll live. We'll learn. So how do I like find out what the payload is from here? Oh, so here I do have a message. So this is panic info dot message dot 0 unimplemented. Okay. So maybe I actually want to just look at the message, not the payload. So this is a panic info. Oh, sorry, I forgot to write down what we're doing. Implementing memory management, implementing custom allocator for Rust kernel, and we'll say what we've done so far. Gone over off-stream contributions, and then we what we are doing now. And here we are trying to we've also stubbed out the allocation trait. And now we are trying to debug or show panic messages correctly. There we go. Sorry, I just noticed that was wrong. Okay, so when these panic unimplemented, it looks like the panic info, actually the payload is what we want, despite what the info from the panic macro told us. What we actually want is the message. But this is an experimental API? Why is that? Interesting. So maybe the payload, can we like find out what the payload is here? Panic info dot payload. What does this tell us? Okay, so it's just confused. Yeah, I don't know what this means, but it's not happy. Okay, well, let's see what happens if we try with a message. What was used with a formatting string and some additional arguments returns message ready to be used, for example. Okay, but is there a non-experimental API that gives us that? No. It would be nice if we could find out what the type ID. Oh, we can. Get type ID or self. Okay, well, let's find that out first. And does type ID give us like a name? No. It would be nice if it did, but okay. So let's try. Let's think. So I could just like try to place the message. We know that the message is right. But it would be nice if we could use the payload. So let's Google Rust panic info payload no std. Let's see, just how can the payload of panic be other than something static string? Can only have a string payload. So why doesn't this downcast work? It should. Right, because we're passing a string here. Maybe something's broken. What does this say? This example panics. Yeah, no shit. Interesting. Interesting. Can I do something like, just like show me the whole thing? And we'll kill the current QEMU. And what doesn't it like here? Oh. I need to source my environment to get my cross compiler. Ooh. Okay, so I need memcomp now. So we'll go to my libc implementation and we'll implement memcomp. And we'll write down here that we're implementing memcomp. And let's look at this. We see man memcomp. What do we see here? It returns true if the whole pointer for the size, or not, no, sorry, it returns, what does it return? Our arguments are, let's make it U8 for ease of use. So we'll say 1, or we can't just call it 1, so we'll call it S1, like they do, const U8, S2, const U8, N, U size, and this returns an int, so either 2. And the return value is greater, function returns an integer less than, equal to, or greater than 0. If the first n bytes of S1 is found respectively to be less than, to match, or to be greater than the first n. What does that mean? For a non-zero return value, the sign is determined by the sign of the difference between the first. Oi, oi, oi. If the first n bytes of S1 is found to respectively be less than, to match, or to be. Does this mean that just I have like a sum? Is that what they're saying? So I have like let mute sum equals 0. And then for I and 0 to n, I say like sum plus equals like S1 add I. And then I subtract the other one. And then so like if my string is like 1, 2, 3, 4 and 1, 2, 3, 4, I'll get like 1, 1, 2, 2, 3, 3, 2, 4, and it'll like bounce out. But if this is 5, I will like end up with a positive number, like positive, or if this is 6, I end up with like positive 2. If the first n bytes is found respectively less than, to match, or to be greater than the first n bytes. Oh, maybe it's like sign is determined by the difference between the first pair of bytes that differ. Aha! Aha. So I say, so negative, which size, the sign is determined the sign of the difference between the first pair of bytes that differ in S1 and S2. Okay, so if S1, okay, we'll say let A equals S1 dot add I, like this, and B is the second one, and if A is the same as B, we return A minus B, and we cast these to I32s, I guess, and here we return 0. Which is just like this. And maybe that's right. Okay, so does this build now? Oh, oopsies, this is not memcopy, this is memcomp now. Okay, and then let's turn off the debugger stuff. Hey, okay. Okay, that gives us something. So now this doesn't tell us anything about the payload, unfortunately. But we do have implementing memcomp done. Memcomp libc function may be implemented. We don't actually know if this is verified, if this is like correct. So like not very verified. Okay. So let's print the panic info dot payload dot type ID. Right? I think this is a function they said we can run. And Jesus. And let's just start printing other type IDs, I guess. So any type ID, so type ID of type ID of string, right? Like, what's this tell us? Like maybe like this. Cannot use undeclared, so we'll use core any type ID like they asked us to. And what is... Okay, so it's not that. What about like U8? Not that. Is there like a way to look up Rust look up type from type ID? I don't think it's possible. Great. Great, 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 great. Type name? Or any type name. Ah. Returns the name of a type as a string slice. No, that's not what I want. Type name of val. Okay. Does this give me... Oh, but that'll probably just tell me any. I want like the type name of type ID. Ugh. What about like a non... Oh my gosh. Let's just guess here. So let's say that the panic macro. Well, actually, let's just look at the panic macro implementation. So what I was wondering is this just like giving me a bunch of bytes? Expands to either great. Love that. Okay. So panic 2021. I wonder which version of panic I'm in. Okay. Okay. I just want to know what this is. So it's not a string. It's not a U. It might be a U8 array is what I was thinking. So if I go into... where am I panicking from again? Allocator. Let's try this. We'll panic with nothing. Okay, and is that different than what we saw before? I'm thinking if it's like an array type, then it would be. And it's not. We're seeing 2798164. 2798164. And we're seeing that in both cases here. So here, 2798164. 2798164. And let's go back to running like unimplemented, like this. And here I see, oops, unimplemented. 2798164. So they're all the same. Hey, what happened to my what happened to this guy? How will you guys stay entertained if you don't have a maze on the right, you know? Okay. So all of these said 2798164, which is good. That means that it's not like dependent on the data. It's not like an array that's like U810. It's not like a 10-byte array. It's like something generic that I should be able to match. And so the question is, why is it not a string? Is it like... Is static stir different than stir, like this? Those are the same, okay. And it's not a byte slice like that either. So I wonder what it is. I wonder if it's like format args. Can I look at... Let's look at this. This returns this. My thought is if like in the new version of Panic, they've updated to just providing a list of arguments like this, maybe this is what we're seeing. So let's look at core format arguments. And does that build? It's not that either. Oh, this is so frustrating. Do I really just have to guess? That's so dumb. Can I look at the Panic implementation? No, we already tried that. It uses Panic 2015. So let's look at Panic. So core Panic source compiler built in to Panic 2021. So let's look at this. 2021. Core Panic 2021. Here we go. Oh, here we go. Panic 2021. Okay, so if there's nothing, they call Panic with explicit Panic. If it has like some stuff in there, then they call Panic format. Otherwise, they call Panic display. But all of these do something very similar. So where is this implementation? Where is this defined? Pubconst function panic. In panicking. This is what I want. So here, panic calls panic format. Panic format is defined where? Needed for const value. Oh, here in this file, const function panic format. Okay, here we go. Internal constructor panic impl p. So this is probably my function. If config feature is panic immediate abort, then we just call abort, but we're not doing that. But I did write abort somewhere in my, like in cargo toml. I have this as panic equals abort. What does that do? Panic equals abort. By default, when a panic, the program starts unwinding, blah, blah, blah. Oh, but so memory that was being used will be cleaned by the row system, but we can't do that. So we don't unwind, so we just abort after, but we still call this. So this does pass in. So I was close. This looks like what it is. It should be a, what's the internal constructor here? Panic info, internal constructor, takes in a message, a location. No. Okay, so this is a no payload. And then we just call it. So why call this an unstable feature and then not give me access to it? I was like so confident that the payload is like the way we are supposed to access the inner data because that's what the docs say. But in this case, it's pretty damned clear that it's not set. It's no payload. In fact, we can probably confirm that if we find the no payload type definition. But this is a private type. So we actually, it's just like impossible. Oh, that's so frustrating. Yeah, that's silly. But that's okay. So we do have to read the message. And the message API is supposedly unstable, but we don't have a choice. We have to use it. So, core panic info. So we've confirmed the panic guy. Okay, so I guess this is so stupid. Okay. Whatever. So in main, we enable the feature panic. What was it called? Panic info message. Hello, Alt Tab, get me the right spot. And then in my panic handler, I call panic dot message. So we can say here, if let sum args equals panic info dot, oh, I forgot the API again, message. We, can I print line the arguments just like this, args like this? Else we print line panicked. Sorry. Okay. Why are you mad at me? Cannot find attribute. Do I say like feature? How do I enable this? I thought that was the way. Oh, I have to wrap it in feature like this. Feature. Hey Yosh. Okay. Sick. So we've now implemented panic messages. And what are we doing now? I don't remember. Okay. So now if I go back to my allocator and I say panic, screw you, I should now see that on my screen. Sick. Okay. So we now know all we have to do in order to get this to get the allocator API hooked up is like implement these two little functions, alloc and dealloc. Theoretically, we have our memory regions that are valid. And so now we just have to find a way to do this. So let's look at like what the fuck is in this layout struct. So we are now trying to understand the allocator, the Rust global alloc API. Okay, so what's in here? Global alloc. And in here he passes in a layout of a block of memory. What does that mean? You build a layout up as an input to give to an allocator. All layouts have an associated size and power of 2 alignment. So they're asking, this is like the request. Oh, I see. So they're like, hey, I want like 3 kilobytes of memory, but it has to be 2-byte aligned, which means that I don't just like pick anything. I have to like find a contiguous 3 kilobyte block that's like at an address that's like a multiple 2. Which means, okay, that's pretty straightforward. So this is just the request. So, what I have to do now is I have to find a way to like track what's available and what's not. And what's specifically, I need this to be done without mutable state here, which means that probably I have to use maybe some like atomics to let Rust maybe deal with that. I'm not sure. Gotta think about it. But let's start with like, how the hell are we going to track use memory? Because normally what I would do is I would like in here, if I were just to like be doing this in the standard lib in like a normal project, I'd be like segments, and I'd have like a vector of segment. And in here, I might say like, what would I put in here? I'd maybe put like size, and I might give it like a location or memory offset maybe. And these, hold on, let me pop back open main. So let's not try to allocate a vector anymore so it won't crash. And ugh, it's getting mad at me because I've modified this. So what I would do is like I would take these numbers and I would probably push them in here. So I would say like my segments would look like basically each of these. So I'd have like offset 654 through 36 and put its size as 1024, etc., etc. But I can't do that because I don't have vectors, because I don't have memory allocation. That's what we're trying to implement. And so I can't just like arbitrarily push stuff in. But we do still need some form of like dynamic, I won't call it allocation, but like dynamic storage. Because as I like take memory out of this, the free memory will disappear. And so I'm kind of thinking, without having thought this all the way through at all, what if okay, we don't need this to stay on top anymore. So what if each segment of valid memory, so like this is reserved, maybe this is reserved, this is reserved. Let's draw some vertical lines to make it easier to deal with. What if like right here we put like a block of info, and right here we put a block of info? Or maybe we'll restructure this a little bit. We'll put it at the beginning. So at the beginning of each block, we'll say like what is there. Then maybe I can store like maybe so let's say free and allocated will make them different colors. So red is free. Let's only think about free memory right now. Maybe if I in my allocator store a pointer to this, and this guy stores a pointer to this, and this guy stores a pointer to this, maybe we can just like walk all the free blocks and just pick a chunk of memory from the first block. And then what happens is, say somebody's asking for like this, I could probably in this case, so let's say that orange is tracking like used memory. So at the beginning of each of these blocks too, we'll do the same thing. We'll store the same structures and say like, this is how much memory is being used here. Then here, what we'll do is we'll update this so that we now have this like new used block. No, sorry, that's not true. What I'll do is this will stay the same, the way it was, block of memory, and we'll put like a new block right here. So we'll have like we'll have a pointer here, and this guy will now point to this guy, and this guy will point to this guy. Maybe they don't actually need to point to each other. I think they don't. We'll get to that in a second. But so now we just have like this new info here, and this is now also just boom, 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 and we update this guy to be here, and we update this guy to point over here. Then I think that we have all the structure without needing any like dynamic memory allocation. The only thing is we need to like take a bit of overhead for each block. Okay, so the reason I was going to say that this guy stays here and we don't need to track these movements like this is I think, so if somebody says like, hey, give me an int, I think I can just say like, hey, here's like some static stuff that comes before it. So somebody's asked for this memory, and I'm like, hey, don't worry about it. Like, I'm just going to give you this as well. And what I return is what they asked for, the start of the memory they asked for. But I put like a little metadata on top. And so then when they call free, they're going to call free with this pointer here. And I could just like walk backwards a little bit. Whoop, whoop. And I like know that like the metadata for this piece of memory is at the beginning. Then what do I do on free? I then mark this as like a new free chunk. So this length will maybe stay the same. And then maybe what I want to do is I want to find like which chunks are closest and like merge them if I can, because then I can support bigger allocations. I think all that works. I don't see any major problems with that approach. The only problem is that like I might run out, right? But that's okay. I'm okay with that for now. So, okay. Let's think. So what I need is I need an atomic pointer to the first free segment. So we'll call this first free, and it's an atomic pointer because this needs to be called from like multi-threaded context. Even though there are no threads, Rust is going to be like, oh my gosh, we need you to like write thread safe code. Look, I get it. You're a safe language. That's why I like you. But like, fuck off. Let me do what I want. Anyways, so we're going to make an atomic pointer, and we're going to make this to a segment. And each segment is going to have a... we'll call this free segment, like this, because we were just saying that allocated segments do not need the pointer to the next. So these are going to be slightly different. The free segment is going to have a pointer next segment. And this is going to be a pointer to another free segment, like this. Mutable or unmutable, doesn't really matter. I'll just write mute for now. Think about it later. Okay, so we also we need a way to like initialize this with initialize our global allocator with the multiboot info. So we'll call pug function init like this, and we will initialize it with the info we get from the bootloader. So we'll call this I guess we probably want this to be all uppercase because it's a global static. We say alloc init info, right, like this. Okay. Then here, maybe let's get crazy and convert it into a reference so that we don't have this like pointer code leaking everywhere. Okay. And then here, we take in the info. So info, multiboot info. This won't compile because I put an extra bracket here. It won't compile because I'm missing things from here. So first free will just be a null pointer to begin with, which I think is core pointer null mute or something. It's mad because I haven't imported this, so we'll use create multiboot info like that. It's also mad because I haven't used this like pointer type, so let's sync atomic pointer. Sync atomic pointer. Okay, and now it compiles. So now we have to figure out what the fuck goes in this init function. What we're doing now, implementing a global allocator. Okay, so what do we need from here? We have this existing function in the multiboot class, which is print the available sections. And so probably what we could do is we can just say info. We want to like request an iterator of these things. So info mmappable sections. I'm now remembering that there was something odd about the data that was coming out here, so I want to do like just do some sanity checks on what we walked last time, because let's show it. So here it says that there's like 144 segments, but I'm only printing 1, 2, 3, 4, 5, 6 of them. And if I take out this like filter, it's like a lot of like 0, 0, 0. first of all, the size of this thing, if I understood correctly, was supposed to be like static, just the size of the struct. And then also, like, what the fuck is this? So I did want to confirm. So I wanted to do a couple sanity checks. One was I wanted to add up all of these lengths and see what they come up to. So let's do that now. So let total length equal 0. And we need to take the length of each of these. First of all, I read something on the OS wiki saying that putting U64s in here might cause like deserialization issues. I didn't see those, so I'm just gonna put them back. And this is len adder. Okay, and then let's add these up. So we'll say total length plus equals len. We'll take out this print, and we'll here just print at the end. Total length is total length. This, which should give us something. So that gives us a big number. And let's do total length as F32, because I want to be able to like put this in gigs. Divide by 1024. Divide 1024. So that'll give us in megs how much we have. 127 megs. That's nada. Nada. Let's see. Let's see. If I walk all 144 entries, I get something, but like these are clearly garbage info, right? This size is supposed to be the size of the struct, the multiboot mmap entry. And this is like totally fucked. So maybe that means that what we're parsing here, this mmap length, is this possibly wrong? Maybe. Maybe. So we know that this, like, we can do a sanity check here where we look at this guy, and if he's right, then we know at the very least that, like, at this point in the struct, we've got the right number of bytes. And so everything before should hopefully be okay, unless we have, like, 2 errors canceling out. So let's try that. So we can print line, this is like the info.bootloader name, and we need to like create a stir from this, I think. So let's look up. Is there like there's like a from pointer lang or something, I think. From pointer length. Or maybe like a from slice. Okay. So string methods. Come on. There's got to be one that's like construct me from a slice. Oh yeah, slice unchecked. Deprecated. Bypass exhibit. Use get unchecked. Begin end. What is that? Stir get unchecked from an I, where I is a slice index. What the heck? Returns an unchecked subslice of stir. Oh, but I don't want us. I want to go the other way. Sorry. I want to take in a slice and give me. See also the stood stir. Ah, this is what I was looking for. From UTF-8 unchecked from this, and then probably these U8 slices can be constructed out of pointers. So core slice from raw parts. This is what I was looking for. Okay. So we'll call this the bootloader name slice is core slice from raw parts. And here we take in the bootloader pointer, the bootloader name pointer, sorry, and the length, and here we'll just say for now. but I'm not really worried about it. Does that compile? Yes. Okay. Then, sorry. Then, we need to convert that to a string, which was let bootloader stir equals core stir from UTF-8 unchecked. And here we can just pass in bootloader name slice. There we go. And does this compile? Yep. And then we can print the bootloader stir. And this says QEMU, which is like a sane name for a bootloader that's being loaded by QEMU. So I think that's fine. That means that we can be like fairly confident that at least at this point in our struct, the memory layout is sane. And we can also be pretty sure that like the mmap adder is at least somewhat sane because we were getting like sane info up until the point where it was just zeros. So let's look at the, what is it called? It's called multiboot OS dev. Let's look at the documents for multiboot and see if they define this like zeros thing. So this is down here somewhere. Num size. This is the one. So if bit 6 in the flag were set, then the mmap star fields are valid and indicate the address and length of the buffer containing the memory map of the machine provided by the BIOS. Mmap adder is the address, and mmap length is the total size of the buffer. The buffer consists of one or more of the following structure pairs. Mmap length is the total size of the buffer. So, okay, sorry. So this mmap length is 144, as we saw. But this is the size in bytes. So we actually need let num mmap set adders is the mmap length, which is mmap length over the size of the struct. So that's core mem size of multiboot mmap entry. This. And so then here we should iterate over to num mmap adders. It doesn't like U32 over U size. Man, sometimes I like Rust, and sometimes it's annoying how explicit it makes. I've like, you know, it's like right. It's right to make me argue with it, but oh, it's annoying when I don't want to. But it does prevent a lot of bugs. So okay. So that's good. We have no more of these like invalid elements. It is still weird to me that we only have 127 megs. Is that right? Total length over, what's the unit here? Length is size of the memory region in bytes. Yeah, that's fucked. Why do I only have 127 megs? As a 32 divided by 10, 24. Oops. Okay, so let's stop printing this total length and let's just try seeing. Oh, this. Let's fix this as well. Just sorry. Num mmap adders. I just want to print this in terms of elements instead of byte length because nobody cares about byte length. This is info. This. Okay, so we have 6 entries. Entries come in at 639K, 1K, 64K, 129. So this is like 127 megs, 128K, 256K. So why is that? Why is that? Is this because QEMU is only giving me 128 megs? QEMU system set memory size. Aha! For instance, default 128 megs. Okay, so maybe this is right. That's surprising. So let's just like chuck in a like I don't know, 256 M. And print the total size again. Total length plus equals. What was this again? Star_p.len. And here we wanted to print the total length as total length as a float divided by 1024 divided by 1024, so we can get this in megs. That's pretty good. That's surprisingly good. Yeah, that's sick. Okay. Wow, okay, so this is working. So we've double checked the memory ranges provided or parsed from multiboot info. Okay. So now all we have to do is go through that like linked list setup where we say for each of these chunks that we got in, let's drop in a free segment header. Oh, I also read somewhere. Fuck. Okay. So our kernel is actually in some of this memory. Because the bootloader just shoves in our binary at 1 megabyte. I think. The OS Dev Wiki said that's by convention, but I saw somewhere else that like it does that, and also it makes sense with the linker script. So if I like look at the linker script, if I look at here, so we like say like, hey, don't put anything out for the first meg. Then here's my text and data. And so I assume that this is where the kernel is. I wonder if we can check that. Is this like .text a symbol that I can like look at? If I remember correctly, there's like a way to put in my linker script like variables that I can just access from code. Linker script extern variable. Okay, so yeah, so you just put a label in there. Right, so I can actually in my linker script here I can just say, hey, where's like my kernel start at? And let's put a semicolon, I guess. And where's my kernel end at? And then in main, I think there's a way for me to like say I have like external functions. So it's like extern c kernel start, something like this. Does this like compile? Cargo build. Oh my gosh. Does this build? No. Okay. Rust define external variables. Extern C, no mango. Yeah. This is what I'm looking for. So this is kernel start. And calling this a const U8 seems fine to me. Or can I just call this a U32 actually? 32-bit addressing. Sick. And then we'll do kernel end as well. And let's print out what those are. So this is kernel start. And let's just shove kernel end in here as well. Oh, it doesn't like that. Oh, because I spelled Kenrel. Kernel, not Kenrel. Okay. And what was the command? qemu. So why? Oh, oops. Kernel start kernel end. No. Unless it's backwards? No, that doesn't sound right. Oh, is it actually that I need like the address of these? To get a point at the start of yeah, okay, sorry. So I actually need to take the address of this as so can I just make these like say these are nothing. These are 0-byte types, and I actually only want their addresses. This as const u30. This as a const pointer. But we can't format those, so can I maybe format them as debug? Hey, there we go. Okay. So can I put, let's print these values in hex 2, and we can see if any of these blocks, like, match up with where my kernel starts. So this does line up, right? So this is 1, 2, 3, 4, 5, 6. So I think this is 1 meg. What is, Python? So that was 0x1, 2, 3, 4, 5, 6. Divide 1024. Divide 1024. Yeah, so that is 1 meg in. So that lines up with the linker script. And it also lines up with the concept that my binary loads these segments at those physical addresses in memory. Very cool. Very, very cool. Okay, so we now have symbols for kernel start, kernel end. We can like find out where those are, and let's print these as hex. I think there's like a way to format Rust format hex. I think you just like shove like an OX in there or something. Oh, Jesus. Wait, so what's the difference between these? %04. Oh, I see. If I want the leading OX. So the 04 tells me how many digits I want. So percent or $sign or number sign. Oh, Jesus. It's adder %04 X. What was the difference between positive and lower X? Oh, with positive, I want big letters, I think. Hey, okay, here we go. So, yeah, my big block of memory that I'm allowed to interact with is this one here, and it does in fact start with my kernel. So if I just like pinch these as allocatable blocks of memory, I would just start clobbering my own RAM and we'd be in a shit show. So for now, let's just block that off. So is there anything else I need to worry about? Oh, the other thing I wanted to check is in my VGA implementation, I just like start using this buffer at like 0xb8000, and I don't know what the fuck that is. So that would end up somewhere in like this range. So it does seem like it is true that like if I just mapped all of these sections, I wouldn't clobber my terminal. So that's like another good indication that I'm getting the expected output here. Okay, so let's just assume that we can use all of these blocks, and maybe yeah, let's just assume we can use them all. It is kind of weird that there's like this like 128 and 256K block at the end. I expect that there's some reason for this. Like maybe they expect a 64K or 640K block to be like our page tables or something. And so maybe they put those at like specific addresses. So we don't have to worry about them. So for now, maybe what I'll do is I'll just find the biggest block of RAM and say like, that's what I'm going to use. Because I assume that like these are like very specific sizes. And I am sure that there's a reason for that. So let's just take the big block and we'll say that's our fucking heap. Yeah, let's do that. So in our allocator, Oh, I guess the other thing we have to take into account is where the fuck is our stack? Where do I set that up? So in my initial boot sequence, I create a stack in BSS. Can I, like, print the value of ESP when I start? Because I should, like, reserve... I should make sure that I'm not colliding here. So here, my stack top is ESP. Call kernel main. Okay, so let's just get like an approximate here. In kernel main, it would be nice if I could just like read the register of ESP. So I think that you can make like a naked function here that says like, hey Rust, don't like fuck with me. Let me do what I want, please. And in this, I can just say, I can make this a function, which is like get ESP, which will return a U32. And in here, I can probably just do some inline assembly to get that. So let's look at the inline assembly Rust. And yeah, you just boom, ASM macro. They let me specify registers. Temp equals out reg. Okay, so like what is the syntax here? Oh yeah, let me just like parse this like fucking syntax tree. That's great. Like I don't oh god. Just give me some examples. Okay, out reg can be can refer to a register class or an explicit register. The allocator register name is substituted in the string. The allocator register will contain an undefined value at the start of the code. So will this like do... Does the ASM macro... Is it like... How smart is it? I kind of want it to be dumb as fuck, right? Because like it might do something like if I call ASM and I say like, hey, I'm going to put this register in there, it might like back it up. And I don't want it to do that. But I guess there's only one way to find out. So our ASM instruction that we want is we want to copy ESP into the return register, which if I remember correctly is EAX. C decal x86. So this is the calling convention that we're using if we understand correctly. And it says that return in the EX register. Okay. So let's do an ASM block. And we'll just move. Then we want to make sure that this is HET syntax, because this is what I was using. Basically, I don't know either of them, but the example that I got when I was starting here in boot.s from the OS Dev Wiki, this is AT&T syntax. So I'm just going to keep it this way. So that I'm only having to learn one. And so this is source to destination. So I want to move ESP into EAX like this. And like theoretically that's it, right? So if I cargo build this, does it compile? Oh, you're such a bitch. Okay. Let's do this. We'll just fucking define the function here. So we'll just do the same thing here, and we'll just call this get ESP like this. And we'll do move ESP EAX, right? And then here we'll like just say, hey, there's a function defined somewhere, don't fucking worry about it, and it's called get ESP, and it returns a U32. Does this compile? Okay, that compiles, that's good. And so now here, if I say, let's print line get ESP, or let ESP equals get ESP, and then let's print line that. Let's see what it says. Misaligned pointer address. Pointer dereference. I'm not trying to dereference shit. Address must be a multiple of 2, but is that oh, maybe I need to align this function. No. Who thinks that I'm trying to do anything? Like, I thought that this is safe. Okay, can we obj dump dash d target debug, and let's look for get esp. Get esp. Huh. Oh yeah, it's in here. And it is in fact just a move of, maybe I did get these backwards again. Let's just there's some heavy room for fuck up. Okay, so that's definitely not it. You can tell that I had the order right because I'm just jumping my stack all over the fucking place. That's so funny. Okay. Okay, so this is right. And I'm surprised that this doesn't work. I was kind of hoping I could just yoink the value out. And I wonder if it's because, like, EAX, integer values of memory addresses are returned to EAX, floating point, blah, blah, blah. EAX are caller saved. Sure. Sure. So, like, here, when I call this, I should push EAX, and then I should get it back, and I should pop it. If I don't print this, does it still panic on me? Yeah, that's really weird. Is it really just this function call? It is. So, like, why? How is this, like, a misaligned pointer access? If I don't do anything else in this whole function... Okay, and... let's just say print here 10. 10. What we're doing now, trying to find where our stack ends. Okay, and is it really just this function call just like fucks everything? Misaligned pointer dereference. What pointer is being dereferenced? The function pointer? ASM define function. Function 0 code jump. Oh, I'm so dumb. That'll do it, dude. Because obviously, if I don't go back to where I called from, yeah, okay, yeah. So here, let's print the ESP, and we'll print this as hex. So this, I think. What don't you like now? Argument never used. Format specifier missing. Cannot find value. Oh. Fine, I'll put a colon here. Gosh, you're so whiny. 113EF. I guess I need to print the rest to make sure that it makes sense. So, we'll do this. We'll get the stack pointer here. And we'll say like this. So let's say stack pointer is here. And 138EXO, which is within the kernel start to end block, which is good. That's kind of surprising. Why is that? Oh, because in boot.s, I say that I want the stack is in BSS. Aha! Okay. So I understand now. So in our linker script, we've said, hey, here is our BSS. And this is part of our like kernel memory space that we want. And here we say, hey, our BSS section, all we have in here is a fucking stack, right? We put the stack in here. And then, so if we then say like, where's our kernel end? It should come after the stack. So that means that all we have to do is we just need to block off this section is used. And never free it. So is that 1 meg before there? Am I allowed to access the stuff at like just before 1 meg? Let's see what it says. So here we have no. That's interesting. So probably what I actually want to do here is I want to allocate a chunk of memory at the beginning of my kernel. Well, okay. Here, I was going to say, let's allocate a chunk of memory at the beginning of the kernel for the segment info block to say like, hey, global allocator, here, this is the memory you want to use and don't use it. But what I can do instead is I can actually just find the chunk of memory that starts with the kernel, then chop off the kernel and use that as my memory block. So let's do that. That seems easier. So I don't have to like fuck around with memory layouts and stuff. Okay. Oh, we're fucking moving. Got a plan. Okay. So in our multiboot parser, where we get the ranges of memory. So sorry, let's just update this. We found where our stack is with custom assembly function. Okay. So now we can go into this multiboot section. We've now got like the code to iterate these, and let's just like factor this out into like a function that we can call on the multiboot info. So we'll call this, we'll say, hey, we'll make an implementation of this multiboot info struct up here. And one of the only function that we're gonna say have on here for now is get mmap adders. And what I would normally return here is I would return like a vector of something. Is that nvim? Sure is. Usually I have it like hooked up to get like some more nice like, how do I call this? I usually have it like hooked up to a language server, but the Rust language server I'm using like crashes when I load it with this like kernel I'm using. So I'm just using raw neovim. No IDE helping me, unfortunately. I wish I did, but yeah, just using it raw right now. Okay, so here we want to get the adders, and usually what I would do is I would like return a vector of like, do I have this here? Of a multi-boot mmap entry. But I can't do that because I don't have an allocator, so I can't make a vector of things. And I don't know at compile time how many elements there are going to be. So like, what the fuck do I do? Rust launch service code. Yeah, it sucks. You have to alt tab to the browser a lot and go into this like, I'm basically spending a lot of time in this docs page. But it's fine. We'll live. We can work with it. Luckily, I've written enough code that I can guess names, and if I just have down here, I have cargo check running all the time, and I just it's usually pretty good at like telling you what you did wrong, right? So if I like say like delete the ends of my print lines, if I like run cargo check here, it says like, oh, there's a similar macro print, and that's not print line, but at least like, I don't know, it's like close enough. It like gives me something. It's good enough. Okay. Get mmap adders. So what I can do though, without any static memory allocation, is I can return this. A slice of these multi-boot mmap entries, because I know that this address is pointing to like a range of memory where these are just like back to back to back. And so I think that I can just call this from raw parts. I can like construct a slice from a pointer and a length, and because this layout matches what is being passed to me by the multiboot, then it should always work out. So I think I can just say I can just take this. So this should actually take in myself. And this should now be self.mmap length divided by the size of the multiboot entries. So this is the number of addresses. This should be a usize, because that's what the pointer length thing is going to ask me for, I think. From pointer core slice. What's the doc called? It's no, from raw parts, which takes in a data and all usize. So here I can just say from core slice from raw parts, and what I pass in here is the address of the memory section, so memmap adder. So here we go, self.mmap adder as a pointer to multi-boot mmap entries, I think, or is it just a void pointer? Const t, yeah. So I have to cast this multi-boot mmap entry, and the length of this is num mmap adders, and we should just call this something we're saying. So this is num num mmap entries, like this. Okay. Does this compile? No, it does not, because it wants this. Oh, I forgot some brackets for my cast. Like this. And here we need this as usize, and we can actually cast it away like this. Oops, I forgot a semicolon. Okay. Cargo check. Call to unsafe function. Oh my god. Yeah, we get it. We get it. I guess I'll just make this an unsafe function, because technically it's accessing RAM just like willy-nilly and hoping for the best. That compiles now, and so now we can adjust our printing logic to say, instead of iterating like this, we can say for entry in star info dot, what's this called? Get mmap adders. Like this. And now P is now entry, and we call this entry.len, entry.size, entry.adder, and entry.len, like this. And let's see if that compiles. It does. And let's see if our QEMU shows something sane. And nice, it's still printing, and we're still chilling. So now in our allocator, when we initialize, we can now just call this fancy get mmap adders, and we want to find the one that correlates with our kernel start. And so like in our specific case of our specific operating system, we know that like that's going to map 1 to 1. So we can just call, I think it's find. Dude, I wonder if like core has these like iterables. Iterator, core iterator. Sick, it does. Oh, it's so nice to work in like no STD, no standard library land, but still have all of these like nice iterator functions and stuff. This is like working in C, you have to like write all these from scratch, but it's so sick that I have like, I'm like writing my own OS and I still have like Rust find. So I have these entries where I want to find the one where entry.adder is the same as our kernel start. Like this. Is it gonna let me do that? Cargo check. Private method. Fine. Oh my god, you're such a whiner. Okay. Fine. Oh, so I need to convert this into an iterator. Like this. Private field. You're just fine. He's public. Expected U64 found this, so we can just do as U64 like this. It doesn't like that, so we can cast this to this first, then cast to a U64. Okay, so we're getting closer. We'll put this in an unsafe block. There we go. Okay, so we now probably will find the right one. So we'll say let big block of memory is the one that our kernel starts in. And let's just see if our big block of memory, what's it look like? What isn't it like now? Print line, macro use, can't find, fine. So we'll import VGA print line, because this is where I wrote it. And no print line in VGA. Cannot determine resolution. Why? I actually thought that this should work everywhere. Because it's exported, so in main, we pull in VGA with macro use. We can use printline here, so why can't, and we could use printline in the multiboot section. So why can't we use it where I am now, in allocator? Because allocator has to be included after VGA. I hope not. Wow, that really is it. Okay, so that's new info to me. I didn't know that like the module include order affects anything. So I guess that there's like a dual pass for most stuff, but for macros, it's single pass. Maybe intentionally. Neat. I didn't know that. Okay. So this needs to have a debug implementation for it. And now it compiles and okay, so here we have some multiboot map-entry, and we found the one at that address. Bing, bang, boom. That's sick. Okay. So now in our allocator, we now have a big block. And let's actually take this out like this. And we will take this print away, and we'll just this, and we'll say if we'll say let big block is the big block but unwrapped, because the find returns an optional, and we'll say we'll just panic if this doesn't work, and we'll say failed to find big block of RAM. And I think this is like reasonable, because if we don't have memory, our whole application just like won't fucking work. Needs a semicolon. Okay. So we found a big block, and now let's just do the sanity check and say that if we put none here, we should see a panic message. Sorry, this is a. We need to actually define the type, so we'll just put this as like, I don't know. Doesn't matter. I just want to test that that expect is doing what they and failed to find big block of RAM. Solid. That does do what I want it to do. So let's just back this out. Get back to the point where we find the big block. Bing, bang, boom. And so now we just need to say the first byte of our the first free segment is the end of this big block. So kernel end is the end of this memory that our kernel's living in. And that minus kernel start is the size of this, but we actually don't, that's actually wrong. We need to take the address of kernel end as a const this. Okay, so let kernel end adder is this, right? And the kernel start adder is the same thing, but as with starts. And so we'll say kernel memory or reserved memory length is just the kernel end adder minus kernel start adder, right? And let's just quickly sanity check this. So this should be around 16K. Oh, it doesn't like that. So this is defined at the crate level. Use of an extern static. Wait, how come I could use this how come I can use this here, but not here? Oh, it's unsafe? Okay, 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 okay. We'll move the unsafe block up a level. Okay. So let's see. 233472 is the reserved memory length. Is that right? Let's see it in kilobytes. So we do that to convert it to K. 228K. I guess that's right. Can I show this? It just seems large, but I guess it is what it is. Maybe there's extra stuff in static that I haven't think about. Because I thought it would be like 16K for the stack. But clearly not. But whatever. That's fine. I don't mind. That looks about right given those numbers, I think. Sorry, let's look again. So is 228 just 139 in hex? Ish. Python. 0x139. 313. No. Okay. I don't know. Does this number even line up? We'll see. Fuck it. No, I should confirm this is right. I should confirm. So let's print this as hex. And let's see what that looks like. Oh my god, what don't you like? I forgot to put a colon here. Fine. Okay, yeah. Oh, because the 1 was part of the kernel. So it should be 39 in hex. Okay, sure. That's fine. We know that this is the same. And so now we can say that our... let's put the pointer to the segment at the first free address. So the first free address is this. Plus start. So this is just kernel end adder. So our new length is the length of the block. So big. Let segment size equals big block length. I think it's called. Minus reserved memory length. Minus the size of the segment. Oh, let's think about this. Is it easier to store the size of the segment with the header included? I think yes. Because that means that like when I check my segment sizes, I can just slot this in there. And then just when I read, I have to like remember. I think it simplifies things. I think. Maybe it's the same. I don't know. That's fine. So we'll just put a note here. This does not include the segment header. No, it really should. It should include it. So minus free se mem size of. Is this right? First of all, I don't have stood, so it's core. Core mem size of, and this is free segment. And really, if I'm just gonna be like dropping this guy into RAM, I should make this a well-defined C packed struct, etc. Okay. So now at the kernel end address, I just drop this guy in here and point the first free to that. Okay, so let's construct the segment. So let segment equal free segment. The size is what we just calculated. The offset is... Oh, this maybe doesn't have to be in here because I'm just there. So I know where I am. So it's just size in the next segment. And so next segment is just a null pointer. Because there's only one block of memory at this point. Okay. And so now I just write this. I need to write this out into RAM. So I say, oh, I should actually probably just say that this is the create kernel end as this, right? Because like I want to write to the RAM directly. And then I can say segment equals free segment like this. Segment. Does that work? It doesn't like that. What if I do this? What if I do this? We're pretty close. Pretty close. I always forget to put these like double colons at the end of the functions, because in C++, you just call templates with their angle brackets directly, but in Rust, you have to like put these double colons in there to disambiguate between this and like something like less than. So it's like you're trading this like syntax for easier parsing and less ambiguity, which is like kind of nice because in C++ you get these like, oh, sometimes you have to put a space, sometimes you don't. But man, I forget this every fucking time. Every goddamn time. Segment size and zoom size. All right. We're close. Oh my god. Okay. Just fixing up some type bullshit. Reserve memory length. Oops. Maybe this is the one that needs to be size. Assigning to and T is undefined behavior, so maybe I have to do it like this. Casting happened here. Maybe I can like trick the compiler like this. Yeah, okay. So what's actually complaining about there? It's saying that this is undivided behavior. Okay, fuck off though. Oh, maybe I just do this? No, I can't have this. I don't know. We'll see. I'm sure that there's a good chance that this is gonna come back to bite me in the ass. I'm like almost positive of it. But if it works for now. I'm sure. The Rust like rules around const and mute. It's like it always confuses me once you get in here. And I know it's like actually, I think if I understand correctly, it's like harder than C in a lot of ways. Because in C it's like a well-defined thing because you're always doing it. In Rust it's just kind of like there's no spec and it just goes like let's go with the flow, see what happens. And yeah, if you like create, it's really easy to create something that's like not sound for Rust, which sucks. Oh, okay. Well, it doesn't like these, so let's just make them U32s, I guess. And all of these, like, const, bracket, these need to be placed with const U32. And this is in main as well, so I have, like, the same problem. Oopsies. I ended up with these like double star consts as well, which is annoying. So let's just pop those guys off. And now does this build? Oh, I didn't save. Okay, we build now. And so now what I actually probably want to do is I just want to see if what I wrote is like stuck. So let's pop open GDB again. Like this. And we'll pop open GDB. Sorry. GDB is not installed, so we just quickly refresh my dev environment to get him back. Come on, baby. Okay. Rust GDB. And now I connect to the QEMU GDB instance, which is target remote localhost 1234. And now I just want to break at kernel main. Continue. Single stepping until exit from start. Oh, I bet you that get ESP call just like totally fucks up the debugger. That's pretty funny. Okay. It's okay. We don't need this anymore. That's so fucked. So let's start up duty again. Break kernel main target remote localhost 154. Continue. Next. No, okay, this is just like fucked. I guess single stepping won't work. So we'll just have to like write down. So I want to do it at 47. Rust GDB b main.rs47. We restart the QEMU. We connect to the localhost. Target. Oh fuck. Info br del2. Target remote localhost 1234. Our breakpoint set. Hit continue. And now we want to print the memory at 139000. So print 139000. And we have to cast this to a const free segment. Maybe I need to say this is allocator free segment. Unexpected token. Okay. Well, we know what the memory layout should be, so let's print. Oh, do I know? We have a U size and a pointer, so we should see. Let's just call this like a U32. Is it like this? Const U32. Oh my gosh. Can I not cast to something? I just want to cast to a pointer. P info. What is, okay. P mute U32 at 139000. Unexpected token. Why? That's, oh, god damn it. God damn it. That's so stupid. That's so dumb. Can I do this with like non-Rust GDB? GDB target kernel debug kernel bmain.rs. All I want to do is check if the RAM's right, man. What line is this? 47. Target remote localhost 1234. Continue. Okay. P info. Okay, so P void star 0x 13900. So no symbol void in current context, but we're getting close. So if I do a U32 star, no. U int 32t int star. Come on, give me int. Oh, god damn, dude. Okay. Why can I really not in Rust GDB cast a pointer? Rust GDB cast to pointer. So do I need a variable as star mute? Oh. Oh. I can use Rust cast syntax. Oh. Okay. You know what? I'm not mad anymore. I'm not mad anymore. You got me. I just didn't read the docs. Okay. So here I should see a size, and can I do +1? Okay, so I see a size which is about 512 megs in that chunk of memory, and I see the null pointer in the next slot, which means that this is working. Okay, so now all I need to do is I need to update I just need to write the allocator deallocator functions. Easy peasy. Okay. So alloc. Okay. So what does this guy do? Let's reference this beautiful drawing. So we have this block here, and we are like inserting a new block here. So we need to update this guy's. Sorry, we're not doing that. We're inserting this block. So first, we need a used segment, which all it has is the size. And we're going to insert this here. So first we need to find a free block. So let's walk the free blocks of RAM, and we'll probably we'll just do it. We'll do it in line for now, and I'm probably going to regret that and want to split out a function later. So how do I do that? Self. Oh, I never assigned the allocator first free. So self.first free equals atomic pointer new. Oh no, I have to store this in the atomic store, and we'll just call this segment as. Oh, we just do this segment like this. Does that compile? Let's see. Oh, check. It doesn't like that. Store argument. Oh, fine. Ordering relaxed. Every time I use atomics, I know that there are these like ordering constraints for when things conflict. And every time I'm just like, I don't know, I don't care. And maybe I shouldn't do that. Maybe, but in this case, I know that I'm only ever setting this once in the context of my entire program. So it's fine. We'll make it work. And here I need the ordering type here. Give it to me. Nice. All right. So when I allocate, let's walk the first three blocks. So impl allocate, so function. No, it's fine. For while, what am I even trying to do? I'm trying to walk the blocks. So self first free load. Oh no. Oh no, it's okay. First free will never change. It will change. It will change when I've allocated, right? As soon as I allocate the first time, if I allocate from the front, this block is going to move. Unless I allocate from the end, then it doesn't. So I'm thinking, like, do I have to worry about atomics here? First of all, no, because this isn't multi-threaded. The reality is that, like, no matter what I do here, it'll work. But I'm just trying to, like, think, is there a way to avoid it? So, okay, that's fine. So we'll call this first, let iter, a free block iterator, I guess we'll call it. And we'll load with ordering relaxed. Here is actually probably where we would want to say, like, no, give me like the fucking latest and greatest. Like, don't give, there's a very strict ordering requirement since I need the latest. But it's fine, we'll leave it for now. And I think this is it. So we're gonna, this is a pointer to the first thing, I think. Let's see, cargo check. And let's print line free block IT. Like what, or let's use the trick of let this equals free block IT. It's gonna get mad and say, I can't assign that to that, but it'll tell me what it is. Mute free segment. Okay, good. So this is a segment. Now we check the layout requirements. So we say for while free block IT, is there like a null thing I can like call in this? Pointer rust. So in the primitive pointer, do I have like a is null? Is null, nice. While it's not null, we check. Here we just say failed to allocate. Right, we're gonna assume that if we're walking all blocks, by the time that we get out of here, that means that like we didn't find one. And now we need to check the layout constraints. So the layout has size, align. These are the two values. So let size equals layout, size, let alignment equals layout dot align. And so now we just have to say if, so we want like the first free address. So let's just say that adder, the block address is free block it add 1. I don't know, so it depends on if the block iterator, if this like add function works in units of bytes or if it works in units of elements. So let's just check that. Well, let's just make it work in bytes. So free block it as const u8, right? U8. And then let block adder equals block adder. This needs to be plus the size of the free segment, or mem size of free segment. Right, this is where the block starts. We'll call this requested size and requested alignment. And now we need to like increment the block address until the alignment matches. Right? Because our first free chunk of memory is over there. No, sorry. Let's think about this. So what I've just done is I've found like an address in here. But actually, like the chunk of memory I give out is actually going to start with my free block. I'm actually planning on moving this block forward like this. Which means that what am I trying to reserve here? I need chunk for my header. And let's kind of like, so I'll have my header here. And I will make no requirements for alignment of my header, right? Then I will like increment or decrement this area before returning this area to fulfill alignment constraints. And that just means that I'll have to be careful about reading this structure directly. I'll have to copy it. But that's okay. So let's try that for now and just kind of see what happens. So first we need to see if my block, if my free block it, if the size of this thing is not big enough, is less than requested size. Continue. So this is what I was gonna say. Like if it's too small, like continue. But we also have to like check the alignment first. So it's probably easier to split this out into a function. So we'll say function check get returned pointer for segment is the free segment, and the layout is the layout they requested, and we'll return an option. And what do we return here? We can just say option mute u8 for now. And this is actually wrong because we actually need to return two pointers, right? One is the pointer to the block that we want to write for the metadata, and one is the pointer that they're going to use. And let's just wrap this in a struct. So, like, we'll call this alloc. We'll call this, like, we're about to allocate this. So, pre-alloc metadata or something, and we'll say one pointer is the header, right? We can just call this alloc metadata, and the other block is the pointer. And we'll say this returns an option alloc metadata. Okay, let's quit this. We don't need this open anymore. Quit, exit, 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 please. And so first, if layout.size is, if the free block size segment.size less than layout size, we just return none, right? That's the first obvious check. Then we get the segment size, or the segment start, and we check its alignment. Well, so no, that's not true. First, we need to allocate this area for the header. So that means that the segment as const free segment, let's look to the header equals this, and then we have to do some trickery to let this cast rail. So header as u32, and we'll say, okay, that's fine. Then we now need to find like the pointer starts. So let pointer equals header plus layout dot no, we need to remove the size of the header, right? So core mem size of, and this is just a used segment, like this, segment. And now we just need to increment this until the alignment's right. So we'll say this. We'll say pointer needs to be incremented by pointer percent layout dot alignment. We need to increment this by layout dot alignment minus this, right? So like if we were 1 byte over, this would return 1, and so we need to increment 7 more bytes. We'll call this alloc addresses. I like that better than alloc metadata. And now we can just return that. So we can say alloc addresses. Oh, well, first we need to check. So if let's see. Pointer. So segment.size minus pointer minus header, right? So like how far have we moved from the segment size? Less than layout size. We return none. Otherwise, we can return our addresses. Like this. And the header is header as mute u8. And pointer is pointer as mute u8. Okay. So now we just say let pointers equals get alloc addresses like this, and we pass in the free block iterator and the layout. Does this compile? No, it does not. We'll just do some casting. Just do some casting. Just do some casting. No, implemented for fine. Help, there's no alignment, but there is a line. Plus equals usize, so we'll just cast these to usizes instead. And alignment still needs to be align again. And here it doesn't like this. Pointer header is usize. This is ambiguous, it says. So we go like this. And we probably actually don't need this cast at all anymore because we changed the types. There we go. Okay, so this compiles. And we say let pointers match. So if we got some, great. Otherwise, we set the free block IT equals free block IT next. We're like the next item in the list. We just try the next segment. And if that's null, it will return. Otherwise, we're good to go. Oh, continue. This. Cool. Okay. So now we should know if this is like an allocatable chunk of memory. So like, can I just like print in here? Bound chunk. And here, let's make a vector. And we'll try to put something into it to force an allocation. What doesn't it like here? So this is alloc vec new cargo run, or this is not cargo run, this is qemu. And fuck the debugger. Okay, so this just says failed to allocate. So it actually never found a chunk. So let's try to debug why. Print line, segment size too small. And this is segment size too small after header reduction. It just says failed to allocate. Okay, so that means we just must not be iterating. Which makes sense because we're trying to use this before we've initialized our allocator. Interesting. So now it's spamming found chunk. Oh, because it's just checking the same one over and over. Okay. 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 So this should just always break now. Nice. Nice. Okay, so we have our pointers, and so now we thinking. So we now know that our use segment size is going to be from the start to pointer plus end plus size. So we say pointers dot pointer plus as usize, right? Plus the layout.size, right? Is that the right value? Right, so this is going to be the end, right? Which means that our metadata now is going to have the size as the end minus the start. So let meta size equals n minus pointers.header as usize. And now we can say pointers.header as used segment, like this, equals used segment size meta size. Okay. So that works. Now I'm almost positive we're gonna have some like alignment issues here later. But for now, I don't give a fuck. And more importantly, we have to copy the data here. So what we have right now in the header block here is the free data. So we actually have to say pointers.header as, oh, this is stupid. We don't actually need this to return the pointer because we know what it is already. Well, that's okay. It's fine. It's fine. Free segment. So we need to copy this out. So let segment equal this. We make this mutable. Segment size. Is this what? Is this right? Yep. Segment.size minus equals meta size. Right? So we have to decrease this. And then we store this at the end. So then we say star end as mute free segment equals segment. And unless size is 0. If size greater than 0. And fix me, this is not actually just greater than 0. It has to be if we're bigger than the free segment size. Right? Core mem size of this. Okay, so if we're bigger than this, otherwise, we have to right, okay. So the other thing we have to do here is, now that we've done this, we don't now also have to say that our allocator first free. We have to find, like, who's the pointer to this? Fix me update pointer. Oh! Okay. Let's think about this. I think I'm ready to take a break. And by take a break, I mean stop streaming and think about this. My head I can definitely tell, like, I'm starting to fade in the, and I'm gonna start writing bad code and make stupid mistakes. So what I'm gonna do is I'm gonna call it for today. We got pretty good. We got like a strategy and we got pretty far. And so tomorrow we can kind of like just pick this up and keep going. So let's just make sure that in here I have I've tied off my thoughts. So here, update pointer to point update previous node pointer to point to new head. And here we'll say update previous node pointer to point to next node. Okay, and yeah, I think that's good. We'll just put a note in here so I don't forget. If may need to increase the used segment size if we have trailing memory unused. Size is less than 3 segment size. Okay. I think that's enough for me to pick up on next time. I appreciate anyone who's watched. And yeah, this has been fun. Catch you on the next one. Bye!